This next lecture related to Lab 3 is going to be how to convert the ASCII numbers which people type into the numbers that you would like to use. So, for example, if a person typed a lowercase a, you would read into register AL in that skeleton program, you'd read an ASCII character A, which is a hex 61, and then that's what it looks like in binary. If they typed an uppercase E, that's a 45 in hex. And if they typed a 7, what you would actually see is hex 37, this bit pattern. So this is like essential assembler knowledge that you need to absorb, that everything is just bit patterns. You could think of this same 8 bits as looking like that. You could think of those bits as a hex number like this. You could think of it as decimal 55, or you could think of it as a character 7. Okay, and those are all the same. Got it? Okay, so that same bit pattern has different meanings. And if you typed a character 7, that's what you got. All right. And what you would like to do is you'd like to take these individual hex digits that people typed and turn them into the numerical equivalents. So if they typed an A, you'd like to see in a register somewhere the value of 10. If they typed a uppercase E, you'd like to see a value of 15. If they typed a 7, you'd like to see a value of 7. So how to take this is the data you're presented with and convert it to the numbers that you would like to see. So a couple of ways of doing that. Okay. One way involves subtraction. So if you think of this as hex 61, okay, and B would be hex 62, and C would be hex 63, okay. Well, what's that number? That number is 97. What number do I want? I want 10. So if I subtracted 87 from that, that would work. If I subtracted 87 from 98, I'd get 11. If I subtract 87 from 99, I'd get 3. All right, so that's easy. So here, if our code was we're getting a character into AL. I think that's just all right. And if I later determine that this is a lowercase hex character, A through F, okay, then no problem. I could just say, that's a comment, I could just say, comma, well, that was 97, 87. All right? And that would do it. All right, this one statement does that. Okay. I'm going to suggest another way, which is what real assembler programmers would probably do. So, not that real assembler programmers would never do this. They probably would. But here's another way. Okay. What we're going to do is we're going to notice that the low order bits are the ones that we want. 61 is a 1, 62 is 1, 0, 63 is 1, 1. Like that, right? those bits aren't going to be enough. We could tell. All right, and you'll notice that the uppercase characters are the same. E is going to be 65. Uppercase E is 45. Okay. Uppercase A is 41. Like that. Okay. So if I were to look at only the bottom nibble, actually I really only need the bottom 3 bits, but conventionally you look at the bottom nibble. If I were to look at only the bottom nibble, remember a nibble is half a byte. A nibble is 4 bits. If I were to look at only the bottom nibble, I'd get a number. A would be 1, B would be 2, C would be 3, uppercase A would be 1, so on, uppercase E would be 5, uppercase F would be 6, right? Okay. What happens if I take one of these things and I just AND it with 1111? And I'll take this guy here, we'll use another color, and I'll AND it with 1111. Okay, so this is bitwise AND, which you should all know. And what comes out? 1 and 1 is 1. 0 and 1 is 1. 0. 1 and 1 is 1. 0 and 1, that's a 0. 0 and 1 is 0. 0 and anything is 0. So this part will always be 0. This part will always be 0. And this will be whatever that nibble was. Okay? So if I took B and ANDed it with 1111, okay, let's try that. I'll erase my 7 here. I take a lowercase b. Lowercase b is hex 62, which is 0110, 0010. And I'll AND that with 1111, 0000, and what comes out? 0, 0, 0, 0, 0, 0, 10. That's 2, okay? So this becomes 5, that becomes 2. Alright, see how that works? I'm going to suggest that that's what you're going to do over here. Over here at the label hex, you have no idea whether it's uppercase or lowercase. You know only that it's a hex digit. You can say AND AL, comma 15 or 0xF, like that. Okay. And if you want to make it really clear, okay, you would say 0x0F. 8 bits. If you just said F, you'd get 0F anyway. Okay. And that'll give you a number from 1 to 5. So A was 1. We want to make it 10, right? Okay. B was 2. And so on, right? E was 5. Okay? Like that. F would be 6 plus 9 is 15. And that would do it. So now we've taken our ASCII hex digit, which was either lowercase or an uppercase. Okay? We've taken the bottom few bits of it. We got a number from 1 to 6, 1 to 5, rather. 1 to A, B, C, D, 1 to 6. F, we got a number from 1 to 6. We added 9 to it. We had a number from 10 to 15, which is to say what we wanted. All right. So if I gave you a ASCII digit, A or 1, 0 through 9, what could you do with it? Similar story. Here we have 0 is hex 30. 1 is hex 31. Okay, all the way down to 9 is hex 39. Same story. We could take the bottom few bits and AND them with the F, and we'd have the number. If we just AND it, we'd have 0, we'd have 1, all the way up to 9. Alternatively, we could subtract 48. This is 48. We could subtract 48. Like that. Okay? So I could AND with an F. 9 is 1001. Okay? I could AND with an F and get 9 out, or I could subtract 48 and get 9 out. Okay? So that's how you convert those typed in digits to the numbers you want. Okay, one more short video. We're going to talk about the shifting to accumulate your final number.